Okay, so our third type, or actually fourth type, is going to be the band brakes. Again, this can only use as a brakes, not clutches. So the cone can be used as, which has a table shape, can be used as clutch and a brake. The plate can be used as clutch and a brake. The shoe type brakes only. The band brakes is only brakes, of course. So the band brakes are flexible bands, usually made of steel, is going to be faced with the friction materials that can conform to the curvatures of the drum. So you can see actually in this video that just holding the drum with the band. So the application of the force to the lever will put tensions on the band and forces the friction materials against the drum. The normal force thus going to be created causes the friction force tangential to the drum surface to be created and retarding the drum and stop it. So if we're going to take a look to the parameters of the criteria for the design we're going to have here, the band itself is going to have two tensions, the P2 and the P1. The P1 is going to be the one that's connected to the non-moving parts, which is the hinge, and this will be the maximum value. Then the minimum value is going to be in the other side. That's going to be moving with the level of the lever. The working or the actuating work force is going to be at the end of the lever. Pulling the lever, we're going to pull the belt downward, and this will make it hold the drum. So the angle between the beginning of the belt to the end of the belt contact area is going to be theta. The r is the radius of the disc, and we can find the length for the belt. The length of the lever is going to be L. The distance between the hinge and the pinpoint is going to be A. So the 3-body diagram will show you how we can do the analysis to find the P1, the P2, and according to the W, or we can find the W if we know what the other parameters we have for the system. So design of the banded brake. Start first with selecting the material and specify design value for the maximum pressure. Specify the trial values for the radius, the theta, and the width. Compute the maximum band tension, which is the P1, and is going to be equal to the maximum pressure multiplied by the R multiplied by the width. And compute the tension P2, which is the minimum value, is going to be the P1 divided by the exponential of the coefficient of friction multiplied by the theta. Of course, the theta in the exponential should be in radian, not degree. Just remember that. Then, the torque can be calculated, which is going to be equal to the P1 minus the P2 multiplied by the radius. Finally, specify the geometry of the lever and compute the required actuation force, which is going to be equal to the minimum tension to multiply by the A divided by the L, which is just the equation for the moment we have for the lever. Finally, compute the average wear ratio WR and compare to the recommended values. So let's have an example on that. We need to design a banded brake to exert a braking torque of 81.36 Newton meter while slowing the drum from the 12.564 radian per second, which is 120 RPM. So the solution starts first. First, we need to select the material as we mentioned earlier. So we're going to select the material. We're going to specify for this problem that the P maximum to be 172.4 kilopascal and puncture friction to be 0.25. We're going to propose a value for the radius, theta, and the width, which is going to be as 0.152 meters and the width of 0.051 meters, and the theta to be 225 degree. Then compute the maximum band tension P1. So to do that, we need to actually find the P maximum, the one that we suggested, multiply it by the radius, and multiply it by the width. So we suggested that the P maximum to be 172.4 kilopascal, which is 172,000 and 40 kilopascal. And we have also the R has been suggested to be 0.15 meters and the width 0.05. So if we're going to put all those together, we're going to get 1,333 Newton. Now, we divide that by the exponential of the R multiplied by the theta. Theta is 225 degree, and we need to change that to a radian. So in that case, we're going to divide the 1,333 by 0.25, which is the coefficient of friction, multiplied by 3.93 radian. And this will give me that the P2, which is the minimum tension, is going to be 498 Newton. Now we can calculate the torque. So it's going to be the P1 minus the P2 multiplied by the radius. And this will give me as 127 Newton meters. I can calculate the power now, but I need to find the area first to calculate the wear ratio. So the torque is, in that case, is quite high, and we can either reduce the R or reduce the maximum pressure. It's up to you. Keep repeating the steps 2 to 5 until the radius is going to be equal to 127 instead of the 150 that we calculated earlier. So the P1 now is going to be equal to 1,110 Newton, and then the P2 will be dropped down to 417 Newton, and the torque now can be, of course, be reduced to 88 Newton meter. Step number 6, calculate the working or actuation force. It's going to be the P multiplied by the A divided by the L. So you can suggest that the value of the A to be, for example, 0.27 meters and the L to be 0.381 meters. And thus you can find the value of the work force to be 139 Newton. Finally, I can calculate the area, calculate the power, and calculate the wear ratio. So to calculate the surface area of that disk is going to be the contact angle in radian, and or the ratio or the actually the parameters and the friction of that parameter that has a contact. So it's the theta divided by 360, and this will give me what the percentage of the parameter is in contact, and multiplied by the parameter, which is the 2r multiplied by pi, and then multiplied by the omega, by the w, sorry, the width. So this will be equal to 0.025 meters square. The torque by, actually this should be omega not RPM. So the power is going to be equal to torque multiplied by the omega, and this will give me 1,110 watt. Then just divide that by the area in millimeters, and this will be give you 0.04 watt per millimeter square. So if you're actually going to divide the 1,110 by 0.025, it's not going to be a 0.04, but you should use the area to be in millimeters square. Okay, thank you, and we're going to go now. Okay, we're going to go now to the examples for the tutorials. The first example is going to be about the assembly shown below is going to be stalled by a brake from 775 RPM to 0 in 0.5 second or less. The following data were used to compute the required brake torque. Find the torque. That's the question number 1. You can check the problem 2020, 22.1 and 22.3 for the calculation of the WK square in the textbook. The second example is going to be design the plate hybrid brake for the application described in the example number 1. The friction torque is given as 7.232 Newton meter. Please specify the design coefficient of the friction, dimension of the plate, and the axial force required. You can find the videos available for you after we finish with the tutorial sessions. Thank you very much for the listening, and